Welcome back to Algopk. Today, we're learning about the heap data structure. Now, a lot of students get confused by heaps because they see a tree and an array at the same time. Don't worry, by the end of this lesson, you'll understand exactly how both work together. A heap is a special type of binary tree called a complete binary tree. What does complete mean? It means every level is fully filled, except maybe the last one, and the last level fills from left to right with no gaps. Look at the visualization on your screen. See how the tree is nicely packed? That's a complete binary tree. Now, there are two types of heaps, max heap and min heap. In a max heap, every parent node is greater than or equal to its children. The biggest value sits at the root. Think of it like a pyramid where the king sits at the top. In heap, it's the opposite. Every parent is smaller than its children. The smallest value is at the root. Try clicking the toggle buttons on the left panel. Switch between max heap and min heap. Watch how the same numbers rearrange themselves. In max heap, the largest bubbles to the top. In min heap, the smallest floats up. This is why heaps are perfect for priority queues. You always know where to find the most important element. Here's the clever part. We don't need any pointers to store a heap. No left pointer, no right pointer. We just use a simple array. Look at the array view at the top of the visualization. The root is at index 0. Its children are at index 1 and 2. Their children are at 3, 4, 5, 6, and so on. Here are the magic formulas. For any node at index I, the parent is at index I minus 1 divided by 2. The left child is at index 2 times I plus 1, and the right child is at index 2 times I plus 2. Look at any node in the visualization. Check its index badge. Now use the formula to find its parent. It works every time. This is the power of a complete binary tree. Let's see insertion in action. Make sure you're on max heap mode. Type a number in the insert box, let's say 85. Now click Insert and watch the animation carefully. See what happened? The new element was added at the end of the array. That's the bottom of the tree. But wait, 85 might be larger than its parent. In a max heap, that's not allowed. Watch the comparison display. It shows the parent and child being compared. If the child is larger, they swap. This is called bubble up. It keeps bubbling up, swapping with each parent until it finds its correct position. Either it reaches the root, or it finds a parent that's already larger. The status text at the bottom tells you exactly what's happening. Follow along with each swap. Now try inserting a small number, like 5. Watch, it stays at the bottom because it's already smaller than its parent. No swapping needed. This bubbling up takes O of log n time. Very efficient. Now let's extract the root. Click the Extract Max button and watch closely. First, the root is saved. That's our maximum value. But we can't just delete the root and leave a hole. So here's the trick. We take the last element and move it to the root position. This keeps our complete tree structure intact. But now we have a problem. This new root might be smaller than its children. That violates our heap property. Watch the animation. The new root is compared with its children. We find the larger child and swap if needed. This is called Heapify down. The node keeps sinking, always swapping with the larger child until it reaches a leaf where both children are smaller. Notice the step dots at the top right? They show the progress, and the operation log on the left keeps track of all the swaps. Extraction also takes O of log n time. The node can only sync through the height of the tree. Now click the Peek button. This is the simplest operation. What's the maximum value? Just look at the root, index 0 in our array. Watch the animation. The root pulses and highlights. That's it. No traversal, no comparison. Just grab the first element. This is O of 1, constant time. That's why heaps are used for priority queues. You can check the highest priority item instantly. Now type some numbers in the build heap box, something like 30, 10, 50, 20, 40, 60, 15. Click Build Heap. You might think building a heap means inserting one by one, but there's a smarter way. Watch the animation. We start from the middle of the array and work backwards. Each node gets heapified down to its correct position. By the time we reach the root, the entire heap is valid. The amazing thing, this process is O of n, not O of n log n, much faster than inserting one by one. Watch how the tree gradually transforms. See the comparisons and swaps at each step. Heap sort is a beautiful sorting algorithm. The idea is simple. The root is always the maximum. Extract it. Now the new root is the second largest. Extract that until the heap is empty. Watch the animation. Each extraction is shown step by step. The extracted values appear in the status text. By the end, you have a sorted array. Heap sort is O of n log n and works in place. No extra memory needed. Let's quickly review. Heaps are complete binary trees stored in arrays. Max heap keeps the largest at root. Min heap keeps the smallest. Insert takes O log n using bubble up. Extract takes O log n using heapify down. Peek is O of 1. Build heap is O of n. Now it's your turn. Clear the heap and try these exercises. Insert values and predict where they'll end up. Switch between max heap and min heap, extract all elements, and see them come out sorted. The best way to learn heaps is to play with the visualization. Click around, try different values, and watch the animations. That's the heap data structure. Keep practicing.